Chapter 11, Part 5, the derivative. This lesson will represent our final step in the world of pre-calculus and our first full step in the world of actual calculus. Now we'll start with an informal definition of what a derivative actually is. For now, what I'm going to do is I'm going to say a derivative is the slope at a point. Now up to this point, your understanding of slope has been restricted to slope of a line. We've restricted ourselves to slopes of lines because it's just so much easier to calculate the slope of a line than it is to find the slope of a curve. The slope of a line is just a matter of finding two random points on that line, measuring our horizontal and vertical distances between those 2 points. So this would represent the change in x, this would represent the change in y, and for simplicity's sake, I'm going to start using a slightly different notation. Anytime I want to use the word change, I just replace it with a little triangle. Technically, it's not a triangle, it's the Greek letter delta. So delta x, delta y just means change in x, change in y. So the slope of that line, remember slope is rise over run, so slope would just be delta y divided by delta x, the ratio between the change in y to the change in x. Very easy to calculate slope of a line because that slope remains constant throughout the entire line. If I'm measuring the slope down here, or measuring the slope over here, or measuring the slope over here, or measuring the slope across the entire line, slope is constant when we're dealing with lines. Now I'm also going to start using a different word. Instead of slope, I'm going to say rate of change, because that's what a slope actually is. It's a measure of how fast, or the rate at which, the height of the point changes. So as any random point on this line travels from here, say, to up here, the rate at which the height of those points is changing is constant. It's rising at the same rate all the way through the curve. Where it starts to get a little bit tricky, of course, is when we're not dealing with lines. We're dealing with actual curves. Now, of course, I can measure that same delta x and that same delta y, but it doesn't represent the same thing because in this case, the slope is not constant. If I'm traveling along the curve down here, I'm rising at a much slower rate. Then once I pass this little bend, I'm rising at a much faster rate. I can see it a little bit better if I imagine this end going off in a straight line in that direction, this end going off in a straight line in that direction. If I just look at these two lines right here, I can see that I have a positive slope, but just barely positive, versus on the other extreme, I have a much more positive slope, a much steeper slope than I do down here. So as I'm traveling along this curve, the slope is increasing. The slope is getting steeper and steeper and steeper as I go. So if I go back and compare my curved slope to my straight line slope between those same 2 points, that straight line slope we're now going to start calling a secant line. A secant line, of course, you remember from geometry, is a line that intersects a circle, or in this case a curve, at exactly 2 points. So that straight line between those 2 points we now call the secant line, and the slope of that secant line represents an average rate of change between those 2 points. It doesn't represent the actual rate of change, because as we can see, the rate of change is constantly changing on a curve, but that delta x, delta y can still represent an average of those rates of change throughout that specific interval. The interesting thing happens when I start moving those 2 points closer and closer together. Notice as I move those 2 points closer and closer together, the delta x and delta y get smaller and smaller. And you'll start to see that the secant line much closer resembles the actual curve between those 2 points. In other words, our average rate of change, our average slope, becomes a much better representation of the actual slope between those 2 points. And it begs to reason that the closer those 2 points get together, the more accurate our average slope becomes compared to the actual slope. So at a certain point, this point will be right on top of this point. And notice the delta x and delta y disappeared because we no longer need them, because the 2 points are right on top of each other. And that also means that this is no longer a secant line, but a tangent line. Tangent line would be a line that touches the curve exactly once. And the slope of that tangent line now represents the instantaneous rate of change. In other words, the rate of change at that single instant in time, that single point. Secant line would represent an average rate of change, whereas a tangent line would represent an instantaneous rate of change. And for that fact, it also represents the slope at the point. Problem is, the original question was, what is the slope at the point? When I have a delta x and a delta y, it's just a matter of measuring, and dividing, and I get a numerical answer. But once I get to this point, where the 2 points are right on top of each other, what's actually happening is that the delta y and the delta x are both 0. So I now have an instantaneous slope of 0 over 0, which we, at this point, hopefully understand is not actually an answer. It's indeterminate, which means we need a more advanced technique other than that old slope formula. We need something a little bit more powerful in order to calculate that instantaneous rate of change, or that derivative. That's where something called the difference quotient comes into play. The difference quotient is really just our same old slope formula. It's just a slightly different way of representing it. So what I'll do is I'll take my 2 points and I'll label them x1, y1, x2, y2. Of course, I still have my secant line connecting those 2 original points, and I can figure out the slope of that secant line simply by using my standard y2 minus y1 over x2 minus x1 slope formula. But what I'm going to do is I'm going to make some convenient changes in how I label things in order to make things a little bit easier for me to calculate down the road. First thing I'm going to do is I'm going to define the distance between x1 and x2 as the arbitrary variable h. Now, I use h because I just think that's a convenient letter to use. Some books and some instructors will use delta x because that's truly what the distance between x1 and x2 is. Sometimes you'll see me use delta x, but typically I'm going to use h because h is just quicker and easier to write than delta x. So by defining the distance between x1 and x2 as h, I can now call this just plain old x, and instead of x2, I'm going to start calling that x plus h. Now, since these are called x and x plus h, instead of calling this y1 now represents f of x, whereas y2 represents f of x plus h. So now, since these labels no longer make any sense in relation to what I've labeled my graph, I'm going to go ahead and start making some substitutions. Instead of saying x2, I'm going to say x plus h, minus, instead of saying x1, I'm just going to say x. And of course, what's going to happen with those two x's is they're going to cancel out, leaving behind h, which means the same thing as what I said before. Remember that h is just a fancy way of saying delta x, and delta x is just the definition of slope, delta y over delta x. Where it really gets fancy is on the top. Instead of y2, I'm going to say f of x plus h, minus, instead of y1, I'm going to say f of x. So this right here is what we formally call the difference quotient. Anytime I'm talking about the difference quotient, I'm talking about this formula right here, f of x plus h minus f of x all over h. But remember that the difference quotient is just a fancy way of saying y2 minus y1 over x2 minus x1. It's just the calculus version of the slope formula. Now, the usefulness of that difference quotient comes in determining the slope of the tangent line. Well, right now, remember, it's still a secant line, so the difference quotient represents the slope of that secant line. But as I bring this point in closer and closer and closer to the point on the left, that h value gets smaller and smaller and smaller until a certain point where that h value becomes 0. The point at which the h value becomes 0, of course, is undefined, but the limit as h approaches 0 would represent the slope of the tangent line. So instead of using our old slope formula, where I'd be forced to plug in 0 in a denominator, let's simply think of it as a limit. I'm not actually 0, I'm approaching 0. As the h value gets smaller and smaller and smaller, the slope of the secant line becomes the slope of the tangent line. So instead of trying to evaluate slope using the old formula, I can now evaluate slope using the new formula based on the concept of a limit. So here we have our formal definition of a derivative. Derivative of f with respect to x. F being the name of the function, x being just the name of the variable. The derivative of f with respect to x is the instantaneous rate of change of a function. It's the slope of the tangent line. We find the slope of the tangent line by evaluating the limit. Limit as h approaches 0 of the difference quotient, f of x plus h minus f of x all over h. You'll notice right here some new notation. We call this prime notation. That's read f prime of x. Anytime you see that prime, that just means derivative. F would represent the actual function, whereas f prime would represent the derivative of that function. And another way of representing a derivative, whereas this would represent the derivative at all points, we could say the derivative at a particular point A specifically represents that numerical slope. So given some function in terms of x, I can find the derivative of that function in terms of x, and that derivative would represent all possible slopes at any random point. And then if I plug in a specific a value, that would give me the slope at that specific point. Quick note on vocabulary. When I say slope at a point, when I say instantaneous rate of change, when I say slope of the tangent line, when I say derivative at a point, they all mean the same thing. These are all fancy ways of saying slope. Slope at the point, derivative at the point, instantaneous rate of change at a point, slope of the tangent line. These all mean the same thing. I'm all asking for the same thing. Also, when it comes to notation, we've got a lot of different ways of describing the same thing. I just introduced you to that prime notation. Remember, f prime means derivative, derivative means slope. So if I'm using the old algebra notation or the new calculus notation, it's all the same thing. Also keep in mind that our old algebra way of thinking of slope was the delta y over delta x. Well, in keeping with the fact that the delta y and delta x in terms of a derivative would actually mean 0 over 0, we have a slightly altered notation to that delta y delta x. And we now in calculus call it dy over dx. And yes, the d does still stand for delta, but it establishes a difference. When I'm saying delta y over delta x, I'm talking about algebra 1 slope, y2 minus y1 over x2 minus x1. When I say dy over dx, I'm talking about calculus derivative. It's still a slope formula, but it's found using a different method because we know that this method would result in 0 over 0. So dy dx, f prime of x, those are just calculus ways of saying derivative, and derivative is just a fancy way of saying slope. Some other options when it comes to notation, you might see this guy every once in a while. Remember that I called this the derivative of f with respect to x. This would be the derivative of y with respect to x. This is the same thing as this guy. It's just a matter of pulling that y out of the numerator and saying the derivative with respect to x of the function f of x. Again, all of which mean the same thing. We're typically going to be sticking with these two guys, f prime or dy dx. So let's see how a problem works with a relatively simple one. Find the derivative of the function f, where f of x equals 2x squared plus 4. So what we'll do is we'll start with the difference quotient. Limit as h approaches 0 of f of x plus h minus f of x all over h. Anytime I'm trying to find the derivative, I'll always just start with the difference quotient. The key is now to take the given function, 2x squared plus 4, and plug it in to the two separate parts of the numerator. Now, of course, this part right here is going to be fairly straightforward. It's just going to be 2x squared plus 4. Exactly as I see it here, I'm going to plug it in right here. For the f of x plus h, we just have to be careful. Instead of saying 2x squared plus 4, anywhere I see x, I'm going to replace it with x plus h. So what it's going to end up looking like is instead of 2x squared plus 4, it'll be 2x plus h squared plus 4 for the first part, minus 2x squared plus 4, the second part, all over h. Notice parentheses, I put parentheses because it's following a subtraction sign and I want to make sure that I'm subtracting the entire polynomial, not just the first term. So the hard part is now done. Setting it up is the hard part. The easy part from this point forward is just simplifying, 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 simplifying. Of course, if I tried to plug in 0 right now for my limit, plugging in 0 right here would produce x squared or 2x squared plus 4 minus 2x squared plus 4. In other words, 0 on the top and of course 0 on the bottom. 0 over 0 indeterminate. I don't have an answer yet. I have to simplify. So the first thing I'm going to do to simplify is I'm going to start with this x plus h squared. Of course, you could distribute the negative first if you wanted to. It really doesn't matter the order in which you simplify for these first couple of steps. So I'm going to start with x plus h squared. Of course, x plus h squared means x plus h times x plus h. And x plus h times x plus h is going to end up as x squared plus 2xh plus h squared. I'll then go ahead and distribute the 2, which gives me 2x squared plus 4xh plus 2h squared, and then plus 4 comes straight down. At this point, I'll go ahead and distribute this negative. I don't need to distribute anything across these parentheses, so they will disappear. And I end up with this guy coming straight down, minus 2x squared minus 4. Now here's going to be one of my first checkpoints of this process. If I'm doing this correctly, this next step will always happen the same way. Everything that was part of f of x should cancel right now. Notice 2x squared cancels with 2x squared, and then 4 cancels with 4. If your f of x function, if this guy doesn't completely cancel out, you did it wrong. Go back and start over, because if it doesn't completely cancel, we're not going to be able to do the next step. Everything that was part of f of x, the original f of x on the right side of the difference quotient, should cancel out at this point. So by canceling everything out, I now have 4xh plus 2h squared all over h. Here's why I need everything to cancel. Notice what's left, everything has an h in it. And it's that h that's causing the problem that's producing 0 over 0. That h needs to cancel out. In other words, that discontinuity needs to be removed in order for me to finish this problem. So on the top, I can simply factor out an h. That h on the top now cancels with the h on the bottom, leaving behind 4x plus 2h. Again, if the terms of f of x didn't cancel out, you wouldn't be able to factor out that h, and you wouldn't be able to cancel the h. So at this point, I no longer have an h on the bottom, so I can go ahead and plug in 0 for h, and what happens is I get an answer of 4x, and that's it. That's your final answer. The derivative of that original function is exactly 4x. So what that means for the original function, which I believe was 2x squared plus 4, the derivative of 2x squared plus 4 is exactly 4x. So now if I wanted to figure out the slope at any random x value, I can simply go to this derivative formula, plug in that x value right here, and that would produce a slope for the original curve. Now that you've seen the process, why don't you do it again? Pause here, play when you're ready. So we'll go through the exact same process again. Find the derivative means set up your difference quotient. Anywhere I see x, I'm going to replace it with x plus h for the f of x plus h minus f of x, which is going to be the exact original function restated. So instead of x squared, it's x plus h squared plus 3x becomes plus 3x plus h minus 5 for my f of x plus h minus f of x would just be x squared plus 3x minus 5. As before, the order in which you simplify is really up to you for these first few steps. I'm going to go in the same order I did on the last one. X plus h squared becomes x squared plus 2xh plus h squared. You're probably going to see that one come up a lot. I'll distribute this 3 right here, giving me the inside of the f of x plus h as x squared plus 2xh plus h squared plus 3x plus 3h minus 5. I'll go ahead and distribute this negative now, turning my original f of x function into the opposite of what it originally was. And at this point, I should double check that everything cancels. Don't assume that everything's going to cancel right here. Make sure that everything cancels so that you can be sure that the left side was simplified properly as well. So x squared I see cancels, 3x I see cancels, and 5 I see cancels. Most common mistake on this type of problem is going through and just canceling things automatically without actually making sure that they do indeed cancel. Notice that all the terms that remain on the top have an h on them. Again, if all the terms do not have an h on them, you did something wrong. Go back and find your mistake. So I can factor out an h, leaving behind 2x plus h plus 3. That factored out h now cancels. And now I can apply my limit, getting my final answer of 2x plus 3. Notice I'm not just stopping here and circling this and calling that my answer. I am restating my answer as f prime of x equals 2x plus 3. We've now gotten to the level of mathematics where notation is crucial. If you're not using proper notation and labeling things as they should be labeled, I'm not going to know what it is you're trying to communicate, and I'm just going to mark it wrong because you're not communicating effectively. When I'm labeling a derivative, I should use the prime notation. Here's another one. Go for it. Hit play when you're ready. So this one just as easy as the last few. Plugging and chugging. Simplifying. Simplifying some more. Simplifying some more. Double check. Make sure everything cancels as it should. 2x squared does indeed cancel. X does indeed cancel. All remaining terms have an h on them. Factor out that h. leaving behind 4x plus 2h plus 1. You wouldn't believe how often people do this factorization at this level and forget that there's a plus 1 right there. Cancel out the h, apply my limit, final answer, f prime of x equals 4x plus 1. Alright, so at this point we've established that finding derivatives of polynomials are pretty easy and straightforward. What about derivatives of rational functions? Well, good news, just as easy, and I think just as straightforward, but of course I've done this so many times, of course it's going to be straightforward for me. We'll start with our difference quotient, and this time when I plug in the x plus h, notice instead of it being 3 over x, it's now going to be 3 over x plus h, minus f of x, which is 3 over x, all over h. So notice we have a situation where we have fractions inside a bigger fraction. Here's the point where you need to remember all the way back to Chapter 11, Part 1, the first lesson in this particular chapter. We looked at some limits that involved fractions within fractions. If you want to pause here and go back and look at your notes to remind yourself on what we did when we had a limit of a fraction within a fraction, I highly recommend that you pause here and go back and look at your notes because we're about to do the exact same thing to simplify this limit. So hopefully you'll recall that that method was simply multiplying the top and bottom by the common denominator of the top. In this case, the common denominator of the top would be the product of x plus h and x. So I'm going to multiply both top and bottom by both x and x plus h. Distributing that x plus h across the top, this x plus h right here is going to cancel out. This x is going to cancel out, leaving behind 3x minus 3x plus h. Of course, on the bottom, just like we did way back when, I'm not going to multiply anything through because I want it to be in its factored form. From here, I will go through and simplify the top, distributing the negative 3. And then I see that the 3x's cancel out. Very convenient because all the terms on the top, all the remaining terms on the top, have an h. I have an h on the top. I have an h on the bottom. Of course, I can cancel that h, leaving behind negative 3 over x plus h. Apply my limit, and I end up with negative 3 over x squared, which is my final answer. A common mistake I often see on this problem would be this guy right here. Once I get to this step, some people try to cancel the x plus h and the x plus h, but of course that would be completely illegal. I can't just cancel one term on the top. I can only cancel factors of the top and the bottom. H was a factor of the top, h was a factor of the bottom. X plus h is a factor of the bottom, but x plus h is not a factor of the top because this term right here doesn't have an x plus h. Don't make that mistake of canceling half of a top. Make sure you're only canceling factors. Here's another one very similar to the last. Pause here, play when you're ready. So we'll start with our difference quotient. Plugging in just as before, make sure you're paying special attention to the negative. So I'm going to have a negative 2 over x plus h, and then it's going to end up being plus 2 over x. We'll use the same technique of multiplying by the common denominator. When I multiply across, the x plus h will cancel, leaving behind an x. When I multiply onto this guy, the x will cancel, leaving behind an x plus h. Distributing the 2 allows me to cancel out the 2 x's, which then allows me to cancel out the h. Apply your limit, we have our final answer, 2 over x squared. Hopefully you're agreeing with me at this point that, oh my gosh, this is easy. Takes a while to get through all the steps, but overall, pretty straightforward. Here's another one, why don't you give this a try? Play when you're ready. Start with the difference quotient, plug and chug. Now at this point you're going to have a choice. That x plus h squared at some point is going to need to be multiplied out. You can either do it now or you can do it later. My suggestion is to do it later because right now I already have fractions within fractions. I don't want to make it more ugly than it needs to be too early in the problem. So I'm going to go ahead and start with my multiplication technique in order to cancel out the fractions within fractions. And then at this point, now that I no longer have fractions within fractions, I'll go ahead and multiply that x plus h out. And since I've done it enough times, hopefully at this point you've got it memorized as x squared plus 2xh plus h squared. Distribute the negative allows me to cancel out the x squared. Leaves behind a numerator where every term has an h in it, so I can then factor out the h. H on top cancels with h on bottom. I can now apply my limit, cancels out this h, cancels out that h, leaves behind negative 2x over x to the fourth. But this time I'm not just going to leave this as my answer. I'm going to go ahead and simplify it one more step. X cancels with x to the fourth, leaving behind x to the third, and we will call that our final answer. All right, so at this point I hope you're pretty confident with finding derivatives using the difference quotient. Now let's take that one step further. Let's use those derivatives to actually find slopes of tangent lines. Here we're going to do a two-part question. Part 1, I want to find the slope of the tangent line at x equals 2 for the given function. And then I want to write an equation for that tangent line at that given point, x equals 2. Because we already established in the beginning of this lesson that the slope at a point can be represented by a tangent line at that point. And if we have a line, we should be able to have an equation of that line. So starting with the equation of the function, 2x squared plus 4, hopefully you're recognizing that you've already done this problem. You've already found the derivative of 2x squared plus 4. Just look back in your notes. Are you looking? Are you looking? You should be looking back in your notes. So what's the derivative of 2x squared plus 4? Hopefully you found in your notes that the derivative was 4x. So now starting with the derivative of 2x squared plus 4, which was 4x, to find the slope of the tangent line at x equals 2, let's just plug in x equals 2. So f prime of 2 is 4 times 2, which is 8. So there we go. Our slope at x equals 2 is 8. Now the next question was to write an equation of a tangent line. So to write an equation of a line, we've got several different options on formats to use. My suggestion is always to stick with this. Point slope form of a line. Y minus y1 equals slope x minus x1. If you want to use y equals mx plus b, slope intercept form, go right ahead. If you want to use standard form, ax plus by equals c, go right ahead. My suggestion is point slope because it's easier than the other two. If I want to write an equation of a line, I need two things. I need a point and I need a slope. So it makes sense just to use point slope form of the line. So I've got basically three unknowns. The slope is unknown, y1 is unknown, x1 is unknown. But actually x1 isn't unknown. The x value I'm using is 2. So I've got my x value. I also need my slope and my y value. But again, the slope is also not unknown. We just figured out in part A that the slope was 8. So I've got my slope, I've got my x value, all I need is my y value. To figure out the y value, well, here it is up here. The original function represents the y value. Since the x value is 2, just plug in 2 into f of x, and we get 12 as our y value. Once we've got our slope and our point, we can now write our equation of a line tangent to the curve at x equals 2 as y minus 12 equals 8x minus 2. If you want to go a step further and convert it to slope-intercept, just distribute the 8, add the 12. There's your y equals mx plus b, but I don't care enough to do it. Moving on. Now this is the point where I like to take a step back and point out that we've been doing this the hard way all along, because our graphing calculator will do all of this for us. Now of course, in calculus, half of our exam is with a calculator and half of our exam is without a calculator, so we need to be capable of finding derivatives and slopes with or without the calculator. We've demonstrated that it's pretty straightforward and easy to find the slope without a calculator, doing it by hand, but we also need to know how to do it with a calculator. So if you don't have your graphing calculator handy, pause right here, grab your graphing calculator so that you can follow along. Play when you're ready. Alright, so you've got your graphing calculator in hand. We actually have a couple of options on how to calculate slopes of curves within the calculator. Keep in mind that I'm going to be doing this based on the TI-8384 series, so if you have a different calculator, best of luck to you. Our first option is going to be using the math menu. So from your home screen, just hit the math button. You're going to select option 8, and depending on what operating system you currently have, if you have the newest operating system, it's going to look like the top box. If you have the older operating system, it's going to look like the bottom box. Hopefully you've updated your calculator or you've purchased a calculator recently and it's going to look like the top one. If you have an older calculator, it's going to look like the bottom one, but the key sequence is pretty much the same. Now on that older operating system, it's not going to say derivative, it's going to say inderiv. In just stands for numerical. This is a numerical derivative because what we're doing here, we're not actually finding a derivative, we're finding the derivative at a point, aka the slope. The TI-8384 series of calculator is not capable of actually finding the derivative, so if I give you 2x squared plus 4 and ask you to find the derivative, your only option is to do it by hand. The calculator is not going to tell you that the answer is 4x. What the calculator will tell you is that the slope of the function at x equals 2 is 8. So I can only use the calculator when I'm asking for a slope, not when I'm asking for an actual derivative. So once I've got this on my screen, I'll then type in all the necessary information. Notice the function is 2x squared plus 4. Down here, that's the first thing I do, 2x squared plus 4. I also filled in the blank right here. It's not just some generic derivative, it's the derivative with respect to x. Down here, I put a comma and then an x to tell the calculator that the variable is x. And then over here, that vertical line just means evaluated at x equals 2. So on the top, it says the derivative with respect to x of 2x squared plus 4 evaluated at x equals 2. Down below, it says essentially the same thing, the numerical derivative of 2x squared plus 4 with respect to x evaluated at 2. Hit enter, and it pops out the answer that I got before doing it by hand, 8. So if I have a calculator and I have the option of using that calculator, it's probably going to be a lot quicker from beginning to end finding a slope at a point using the calculator versus if I'm having to find the derivative in general, I have to do it by hand. Now I said there were two options. Let me show you the other option. The other option, instead of using the home screen and the math menu, is to use the graphing feature on your calculator. So hit y equals, type in the function 2x squared plus 4, and then hit graph. You should see the parabola representing 2x squared plus 4 pop up. You may need to hit zoom 6 to get to your standard viewing window. And then hit second and then the calc or calculate menu. It's the same button as the trace button. When you hit second calc, you're going to see this menu of options. You've hopefully used this before for finding zeros, minimums, and maximums, maybe even some intersections from now and again. But now we're ready to get to option 6, dy dx. That's our derivative. And then later on in your calculus course, we'll get to integrals. But right now, we're going to select option 6. When you hit option 6, it'll go back to your graph. If you have multiple functions written in the y equals screen, you're going to want to make sure that y1 is selected. And then just like when you're doing a trace feature, you can go ahead and input the number at which you are trying to figure out the derivative. So we're trying to figure out x equals 2, so I'm going to input 2. I'm going to hit enter, and it's going to pop out the answer, dy dx equals 8. Now, it's really personal preference whether you want to use the math menu or the graphing menu to figure out the slope at a given point. I often use this one if it's a one-off question versus I use the graphing feature if I know I'm going to have to answer several different questions about the same graph. But again, personal preference. All right, let's do the same thing again. New function, but it's not really a new function. It's an old function. We looked at this one earlier. Make sure you go back in your notes and figure out what the derivative is. You don't have to actually start from scratch. But I do want you once again to find the slope and to write an equation of the line. I want you to do this first completely by hand, but feel free to check your answer using the calculator. When you're practicing at home, I always suggest do it completely by hand without any aid from any technology first, and then use the technology to check your answer, not only to check your answer, but also to practice using the technology. So pause here, play when you're ready. So to find the slope, I'll start with my derivative. I looked back in my notes to find when I originally found the derivative of x squared plus 3x minus 5, I found that the derivative was 2x plus 3. Plugging in -1, and I get a slope of 1. Part B, write the equation of the tangent line, starting with my point slope form. I know that the derivative, again, is 1. The only other thing I need is the y value. F of -1, plugging it in, I get -7. Now that I've got my slope and my point, I can write my equation of the line. The end. And for more practice, let's do it again with 3 over x. Pause here, play when you're ready. Hopefully this wasn't too much trouble. Slope is going to be based on the derivative that we found earlier, -3 over x squared. Plug and chug, I get slope of -3. Now at this point, I'm also going to point out the reasonableness of this answer, the slope of -3. If we think about the original function 3 over x is just that reciprocal function. Asymptotes on the axes, and then the curve exists in quadrants 1 and 3. And I'm looking at x equals -1. So a slope of -3 actually seems pretty reasonable to me. I know that within the third quadrant, the curve is decreasing at all times, so a negative slope is perfectly reasonable. I also know that if I had plugged in -2 or -5 or -10, that answer would have been smaller and smaller and smaller and smaller, but always negative. Same thing if I picked a number in the first quadrant, 1, 2, 5, 7, 14, always going to give me a negative slope because they're always pointing down, but the larger the x value is, the closer to 0 that slope is actually going to be. Now to write the equation of the line, slope was -3, y value is also -3 in this particular case, so my equation will be y plus 3 equals -3 x plus 1. Now let's change it up a little bit. Here's a function that we have not yet looked at. It also involves trig. We have not yet done derivatives of trig. I want you to write the equation of the line tangent to the graph of f at pi over 6. Now keep in mind, we have not yet learned how to use the difference quotient when trig is involved. So what I'm kind of implying here is don't do it by hand. Do this one completely in the calculator. Remember, all I'm asking here is to write an equation of the line. So I need two things. I need a slope, which I know how to do in the calculator, and I need a point, which I know how to do in the calculator. So use your calculator to figure out both the slope and the y value, and then write your equation of the line. So I'm going to start by figuring out my y value, and I'm going to do that simply by grabbing my calculator, typing pi over 6 in for x, hitting enter, and I get about 1.047. If you're not getting 1.047, start by double checking that you're in the correct mode. Pi over 6 is a radian, not a degree. Then to find my derivative, I'm going to use either my math menu or my graphing option to find the derivative. It's up to you which route you go. Either way, you should get negative 1.627. My suggestion is to, since we're practicing here, use both methods. Go to your home screen, use the math menu to find your derivative. Go to the graph, use the graphing option to find the derivative. Make sure you're getting the same answer each time. And once I have this, I can go ahead and write my equation of the line using the information I just found. Here's another one. Use your calculator. This time, though, all I want is the slope. So using my calculator, I was able to easily find that the slope was 1/5. Now with this particular function, though, we have looked at situations where radicals were involved in limits. We know how to use that conjugate method to simplify limits involving radicals. You could do this one by hand, and I highly recommend that you do this one by hand on your own right now, but I'm not going to do it because I've been recording videos all day at this point, and I'm tired and I want to go to bed. Enjoy.